Have you ever just stopped and wondered how an AI can recognize your face in a photo, or translate languages on the fly, or even drive a car? It really does feel like magic, doesn't it? Well, it's not. It's a process. And today, we're going to pull back that curtain and show you exactly how these artificial brains actually learn.
All right, so here's our game plan. We're going to walk through this step by step. First, we'll touch on the big idea of how machines can learn at all. Then, we'll dissect a neural network to see what it's made of. We'll watch it make its first guess, see how we measure its mistakes, and then, and this is the best part, we'll see how it actually learns from those mistakes. It's all part of one big, continuous loop.
So, let's kick things off with the one question that really changed everything in computer science.
You see, for decades, we had to tell computers exactly what to do, line by line by line. But the real game changer was when we flipped the script. What if, instead of giving it a million rules, we just gave it a ton of examples and let it figure out the rules for itself? That question, right there, is the entire reason neural networks exist.
Okay, so to understand how a network learns, we first have to pop the hood and see what it's made of. Let's take a look at the basic anatomy of this learning machine.
The most basic part is the neuron. Just think of it like a tiny little decision maker. It gets some information from its neighbors, does a very quick calculation, and then decides what signal it's going to pass along to the next neuron in the chain.
Now, these neurons aren't just in a big jumble. They're neatly stacked into layers. All your data, like a picture or some text, comes in through the input layer. Then it gets crunched and processed by these hidden layers in the middle. And finally, a single answer pops out of the output layer. It's really just like an information assembly line.
Okay, now this part is absolutely crucial. Every single connection between neurons has something called a weight. It's just a number that says how strong or important that connection is. The best way to think about them is as millions of tiny tuning knobs. Learning for a neural network is really just the process of figuring out the perfect settings for all of these knobs.
And along with those weights, each neuron has a bias. It's just a little nudge that makes it easier or harder for that neuron to fire. So if the weight is the volume knob controlling the connection strength, the bias is kind of like the on switch that helps decide if the neuron should even bother activating at all. So here's the wild part. When a neural network is first created, it's a complete blank slate. Every single one of those millions of tuning knobs, the weights and the biases, they're all set to completely random values. The network is essentially born knowing absolutely nothing. It's a clean slate.
Okay, so we've got our structure, and all its settings are totally random. So what happens when we ask it to do something for the very first time?
This first attempt is called the forward pass. It's super simple. We just take our input data, let's say it's a picture of a cat, and we feed it into the front of the network. The information flows forward through all the layers, and an answer pops out the other side. This is the network's very first and completely uninformed guess.
The process is just what you'd expect. Data goes in the front, it works its way through those hidden layers where all the math happens, and a final prediction comes out the end. And since every weight is random, that first guess is almost guaranteed to be wrong. Like, really wrong.
So the network made its guess, but how wrong was it? This next step is all about getting a number, a verdict, on just how big its mistake was.
And the concept here couldn't be simpler. We take the network's prediction, what it thought the answer was, and we put it right next to the correct answer, which we already know. The gap between those two, well, that's the error.
To get a feel for how the network is doing overall, we use what's called a cost function. It sounds technical, but all it does is look at the error from every single guess, mash it all together, and spit out one single number. We call this number the loss, and it's basically the network's mistake score. A high score means it's doing terribly, a low score means it's getting things right.
So, here's the thing. Just knowing you're wrong isn't enough, right? You have to know how to fix it. This next part is the absolute heart of how these things learn. It's the secret sauce.
So this is the million-dollar question, isn't it? The network has this score telling it how badly it messed up. But with maybe millions of those little tuning knobs, how in the world does it know which ones to turn and which way to turn them to make that mistake score go down?
The answer is a really clever algorithm called gradient descent. The best way to picture it is to imagine that mistake score as a giant landscape with huge mountains and deep valleys. The goal of gradient descent is to find the quickest way to get to the very bottom of the deepest valley.
And here's how it works. You start somewhere random on that landscape. Then you look around and figure out which direction is the steepest way downhill. You take one small step in that direction, then you stop, look around again, find the new steepest way down, and take another step. You just keep repeating that process, always stepping downhill, until you've rolled all the way to the bottom of the valley where the error is as low as it can get.
So if gradient descent is the overall strategy, always go downhill, then backpropagation is the engine that makes it work. It's a bit of math that works by starting at the final error and going backwards through the network. It calculates exactly how much each individual tuning knob was to blame for the mistake. It essentially points the way downhill for every single weight in the entire network.
Okay, we've seen all the individual pieces of the puzzle. Now, let's put them all together and see the whole powerful learning cycle in action.
And here it is, the whole shebang. The network starts off totally random. It makes a guess. It calculates its mistake score. It uses backpropagation to figure out how to fix its mistakes. Then it uses gradient descent to nudge every single one of its weights just a tiny bit in the right direction. And then it does the whole thing over again, and again, and again. Thousands, maybe even millions of times.
Now this loop doesn't go on forever. It usually stops for one of two reasons. Either we've just told it to run for a certain number of cycles and time's up, or, and this is the important one, that mistake score gets so incredibly low that we can just say, yep, that's good enough. The network has learned.
And that's really it. This beautifully simple, yet incredibly powerful loop of predict, check, and correct, that's the engine behind so much of the AI that is literally shaping our world today. It all comes down to the power of learning from your mistakes, over and over and over again. Which really just leaves one question. What are we going to teach it to do next?